you might check your book on page 135. Page 135. We discussed this and foreshadowed it a little bit last time. Let me get this buffering.
You might check your book on page 135.
Now. There we go. Got it. All right. So our goal here is to talk, at least the first part of the class, on the buoyant force. All right. Hopefully I spelled that right. Okay, that's the one that I always have trouble. Yeah, anyways. So for the most part, it's easy until we get to this volume displaced. So I like to think of it in three cases. Let's say you have a solid object fully submerged. In that case, the volume displaced equals the volume of the object. So, all right. And just for a visual on that, was it 8 or 7? 8. Right? There. Okay. So we've got this aquarium here. Let's get rid of some of this extra junk. So you can imagine I have this chunk of aluminum. When I put it in here, it's now fully submerged. So while we might not know the volume of this chunk of aluminum, we do know that it's a solid object, it's fully submerged. So in this case, the buoyant force is equal to the total volume of the object. So far, so good? All right. Next. Should get that towel. Oops. All right. Case 2. Solid object partially submerged. So as an example of that, well, and so maybe I'll draw a picture here. The object's completely under the fluid level. Whereas in this case, the object is only partially submerged, right? So in this case, the volume displaced, you could say it in many different ways. You could say it's some fraction times the volume of the object. Now, alternatively, you might say that could be some percent, like 30% of the object is submerged, or 80% of the object is submerged. Again, giving you a visual. We got a 10-pound bowling ball here. This would be a particularly difficult problem, but hopefully you could see that some of that bowling ball is out of the fluid, right? This would be really difficult to calculate that fraction or percentage. Do you agree? Because you'd have to think about, oh, you might have to do some calculus or something, or we maybe have to learn a lot of geometry. So this, typically what we'll do in physics problems for this class is we'll make it easy, and it'll be stuff like it's exactly half submerged, or I'll tell you some percentage that's submerged. That way you don't have to try and do geometry to figure out how much volume is above the fluid versus below. Now, in contrast, if we have a rectangular object like this, that's fairly easy, right? And we'll do this one in a second. If you have a rectangular object, it's actually not as difficult to deal with the geometry. And so that's one of the problems we'll work out, is figuring out the fraction. So you can either figure out the fraction, or given the fraction, figure out the force. All right, more on that. Go back over here. The last one is probably the hardest. when you have hollow objects. So with a hollow object, we oftentimes have to do some fraction of the exterior volume. And this is complicated to explain, so I'm going to go straight to the picture, or straight to the water tank. And so this is the one where we were talking about, imagine you have a boat. Like this. And we put some metal in here. That. And in this case, the volume of the objects involved, the actual volume of metal and the actual volume of plastic are nowhere close to the displaced volume. What do I mean by exterior volume here? You could get the exterior dimensions of the boat and then figure out what fraction of that boat is underwater. And so you get some fraction of, in this case, pi r squared h, right? Now think, pi r squared h, that's the area of this plastic cylinder, the boat, but not all of it is underwater. So as long as you're paying attention to that in these problems, that's it, you should be able to get it. So let's do a couple, see if you catch the tricks, and then you'll know what to do on test day. Everybody got that? All right. So yeah, basically, in my experience, what I've seen is the following. You tell students this first case, and then they always use this for every problem, and then they get the test questions wrong, and you want to strangle them, right? It's important that you know that sometimes the volume displaced is not the volume of the object. That's the most important thing to get out of this. 2/3 of the time, that's not true. Okay? All right. Now, I'm going to give you a conceptual, oh, and maybe I'll say one more thing. How are we going to use this? Well, in most buoyant force problems, the idea is you do an FBD, just like always. You've got an mg, maybe you've got a normal force, maybe you've got a tension or a spring force, and then there's one extra force, this one. And so it's exactly the same as chapter 5, except we have to add in this force, and all the work is in calculating this volume displaced every time. That's it. All right. Okay, let's take a look at 14.15 and try and give you an understanding of this. 14.15, page 135. I'm going to try and give you an understanding of this really quick. So, in motionless fluid, say water that's not got a current, we talked about pressure is equal to pressure at the surface plus rho of the fluid, G times H, where H is depth, not height, depth. We also mentioned at depth, the pressure of a fluid, you could think of that as the same pressure pointing up, down, left, right, diagonal, any different way, okay? So as you go deeper into a fluid, the pressure points equally in every direction. So let's imagine at some instant, and you can see we've got some pictures here. Let's say we know the pressure at the top corresponds to an arrow that's about that size. Furthermore, because this is still basically right at the top, this arrow should have the same size too. As you go deeper, what should happen to the size of these arrows indicated the pressure? What should happen to the size of the arrows as you go deeper? Increase slightly, right? Linearly. It's a little more even. And then the arrows at the bottom should be the same as these big ones, right? What do you notice about the left-right arrows? Balanced. They're going to be balanced. So obviously this pressure will exert a force to the right. This pressure will exert a force to the left. But since there's no pressure differential, no difference in pressure, there's not going to be a left-right force. What about up and down?
Greater magnitude going up from the bottom.
Yeah, and do you agree that it's going to depend on the height of the object? So if the height of the object is h, the pressure down here would be whatever pressure you had at the top plus rho gh. Well, the force associated with that pressure differential, the difference in pressure is rho gh, and then I times it by the area. Well, in this case, delta P, we said, is rho gh, and that's rho of the fluid, not the object. H is the depth, in this case, equal to the height of the object. And what's the area of this? That's a cylinder. What's a good name for the area of a cylinder? If it has radius r. What's the area? What's this area going to be? In terms of r.
2 pi squared.
Careful, 2 pi r is the distance around pi r
Oh.
squared. Yeah, you accidentally, yeah, but you had the right end. Pi r squared.
Oh, I thought we were trying to get the whole.
Just the area of, oh, you're trying to get the sidewall too. Well, do you agree? Again, we don't need the sidewall because the sidewalls balance out. That's why we don't need it. Does that make sense? The rights balance the lefts. So the only area that's going to have a net force on it is due to the top versus the bottom. And there's a pressure difference between the top and the bottom. The top is at some pressure P. The bottom is at some pressure P plus rho gh. So the pressure difference is rho gh. The area is this. Wait a minute. What's pi r squared h?
Of the cylinder.
Yeah, so notice in this case, we have a solid object fully submerged, and this, in this case, happens to be for this case, the volume displaced happens to be the volume of the object. But in general, this force will always relate to the volume displaced. So notice that is the buoyant force. That was our formula for the buoyant force. Does that make sense?
And for the area, the basis.
The area would be the area that is perpendicular to the difference in pressure. So in this case, the area, right, this pressure is exerted on that area. That's why I used that area. If you recall, what was the definition of pressure? Pressure was defined as force over area, right? So, right, if I know the pressure here, that tells me the force per unit area there.
Okay,
Got it? And then I just flipped it. Notice force is pressure times area.
but you are taking into account both the top and the bottom, just in the delta P, right?
That's right, because we use delta P, because really we'd have a pressure down area plus pressure up times area, which is pressure up minus pressure down times area. That's the delta P. Got it?
Yeah.
So we know that the net force is due to these pressure differentials. All right, so now I got a question for you. Going back to the tank. I want you to consider this scenario. Give me a sec. Okay. Got this 14-pounder here. Usually that bowling ball goes all the way to the bottom, sinking. What forces act on that bowling ball right now? Gravity. I agree. mg. What other forces act on it? Normal force from the bottom of the pool. Anything else?
Pressure.
Okay, but what's the name of that force associated with the pressure differential? What did we call it? Not pressure force, but we called it the buoyant force. So in this case, when we've got this sitting on the ground, we actually have a normal force and a buoyant force. Now, to be clear here, the normal force doesn't have to lift the full mg. Do you agree? Just part of it. The buoyant force is helping support some of this, and the normal force as well. So if we do an FBD, what would that look like? Let's take a look up here. Here's my remote. So if we have an object all the way at the bottom, there's a normal force up, there's a force buoyant up, and sometimes I get lazy and just call this capital B, right? So I might start doing that just because I hate subscripts if I don't have to use them. So I'm going to start using capital B for buoyant force. If you want to use F sub B, I'm not offended. Then we've got mg down. Makes sense, right? Now I got another one for you. All right. By the way, when you're looking at this thing, you can literally see how much volume this displaces. I don't know if you care, but for every 6 centimeters of depth, it turns out it's about 8 liters for this aquarium. But just watch the water line relative to this piece of orange tape, and you can literally see the displacement in this volume, right? So as I lift this up, kind of keep that in mind. It looks like it's almost a finger's width above the tape, right? And now notice it's pretty much at the bottom of the tape once it's stabilized. Okay, now I want to do this problem. I'm going to put this in here. We're going to ignore the volume of the hook. This is negligible compared to this volume. Is everybody okay with that? Ignoring the volume of the hook? Okay. Now, let's assume the bottom of this thing is perfectly flat. And no water gets under it. Is there still going to be a buoyant force? In particular, let's go to here. Let's look at our board. Right, so again, I just put a piece of iron in there and let it get perfectly flat, and I want to look back at this thing. Come on, there. Look at this one, right? This derivation, it was critical that we describe some fluid above and fluid below so we get this pressure differential. And now what I'm saying, what if this object is perfectly flat and sitting on the bottom of the tank, and no water gets under there, do you think there's still a buoyant force?
There's still one on the top.
There's still a force downwards, yes, true. There's still forces on the side, true. The pressure still increases as you go deeper, true. But when you look at this derivation, right, we would have a normal force underneath, but if there was somehow perfectly sealed with no fluid under there, what do you think? Buoyant force or not?
So the normal force is now greater.
No, it turns out this derivation is flawed. This derivation doesn't allow us to see what's really happening. Let's go back to the tank. So it turns out this derivation, while it's very nice to kind of get a feeling, is completely false. Okay. Now, so the idea is even if no fluid gets underneath it, you still have a buoyant force. That's what I wanted to point out. And let me show you why we use this terminology. Let's do two things really quick. Look back here. The definition is density of fluid, volume displaced, G. When you put that iron in there, are you still displacing fluid?
Yes.
And so do you still have a buoyant force? That's what I want you to think. Because you could drive yourself batty. Well, what if you put a suction cup on here and whatever? All right, so while I'm getting this fired up here, take a look at the top of page 136. Okay. The sphere, nobody had any trouble seeing the pressure differential, but sometimes with flat objects, people get freaked out and say, wait, what if there's no fluid under there? This FBD is still exactly the same as the sphere at the bottom of the tank. I can prove it to you. Take a look at the water level. We're just above the tape. Do you agree? Just above the tape. And when I remove this, now we're down to the bottom of the tape. So we still had a displaced volume. We still have a buoyant force. Is everybody cool with that? So don't get tripped up by that in your head. And yeah, I talked to a Stanford physicist once about this. And there's some really weird stuff that happens in objects. And you can learn more about that and the pressure anisotropy, meaning the non-uniform pressure. But for now, let's just roll with this. We got a buoyant force anytime you're displacing fluid. Anytime something's under the water, whether it's on the bottom of the tank or the top, you get displacement. Cool with that? All right. So let me go to here. Just to clarify that. So whether you have a block on the bottom of the tank or not, we're still going to get this same buoyant force, normal force, and mg, whether it's a block or sphere or whatever. Okay, good. All right. Take a look at 14.17 right now. 14.17. I'm going to erase the board. You guys try and do that one. Put a star next to that. That's a classic. Make sure you do that before the final exam. 14.17. I'm just going to erase the board for a minute, and then I'll be ready to rock, okay? You can discuss with your neighbor if you want. What do you want to do? Getting this erased. The first erase of the morning is always the worst. All right. Let's go to our tank so we can look at this. I got 3 bowling balls there. So I don't know how this is going to work if you're colorblind, but hopefully you can see we got a 10 with these orange stickers, 12 with the grades, and this blue is the 14. All right, and so when you look at this thing, just showing you, they all, right, bowling balls all have the same diameter. We saw that the 10-pounder floats. In this case, let's assume this 12-pounder just barely floats. Let's see if that's true. You agree that's just barely floating? Can you see that it's not touching the bottom? Verify that? You guys got it? Okay. And then if we put the 14 in there, clearly it's going to sink. All right. And let's read the questions now. Let's see what it says. Which one has the largest buoyant force? We got A, B, and C. I'll draw it up here. All right, so that's supposed to be right there. Help me out. What's the largest buoyant force here? What do you think? It's a tie. Do you agree B and C both fully submerged? Does everybody agree with that? Or that's what the problem says. It's just barely fully submerged, right? So that means it's fully submerged. What's true about the volume displaced for B versus volume displaced for C? They're the same. How does that compare to the volume displaced of A? And then do you agree the buoyant force scales with displaced volume? So it's force. Oops. So it's kind of counterintuitive. The object that floats the highest has the least buoyant force on it because it just doesn't need as much. It's the lowest density. Oh, whoops. Whoops. Part B, rank the densities. Sorry, my bad. Okay. Which ball is the most dense?
C.
C. So that's just straight up, whichever one sinks is going to be the most dense. And then the next one would be B. The next one is A. They all have the same volume, right? But that doesn't mean they all have the same weight. In particular, this was the 14, this was the 12, and this was the 10. So clearly you have more matter per unit volume in this one than that one, than that one. All right, what's part C? Let's do a free body diagram for ball B. Okay, so let's actually work this out. For ball B, how many forces are acting on ball B? How many forces act on ball B in that aquarium? Just two. What are they? Mg. And what supports it? The buoyant force. What's the volume displaced for ball B? It's fully submerged. What would be a good equation to describe the volume of ball B?
4/3 power cube.
Yes. Now, in this case, didn't the problem give us diameter? So let's rewrite that in terms of diameter. What is radius in terms of diameter?
D/2.
And then we got a cubit, which is d cubed over 8. So I believe the buoyant force should equal density of the fluid times d cubed times g over times pi over 6. Did I screw that up? Double check if I screwed that up. The 4 is going to go to a 2 in the basement, so you get a 6. So you get pi over 6. I think that's it. Is everybody in agreement? All right. Well, what's the mass? Ding, 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 ding. I want you to learn a trick, people. This happens in a lot of these buoyant force problems. What we usually do for the mass, rather than writing it as mass, we're going to write it as density of the object times, yeah. So if we rewrite mass as density times volume, and remember, if you're wondering how I got that, density equals mass over volume. So volume, oh, whoops, mass, just rearranging this. We use density as our conversion factor to go back and forth between mass and volume. When I do that, what are we going to get here? Density of the fluid, pi over 6, d cubed g has to equal density of the object, volume of the object, well, that's pi over 6 d cubed times g. We're saying the buoyant force equals mg. That's what I'm saying here, just so you can read this. The buoyant force is equal to mg. So in fluid problems, yeah, it's the same old crap, but it looks a little bit different because we're using density all the time. What must be true? If it just barely floats, what must be true? What cancels out? Yes. So notice, if you want an object to just barely float, its density had better be the same as the fluid. Now, just so I'm not lying to you, you should know that I had to add a little bit of salt, actually quite a bit of salt, about a little more than 1 kilogram of salt to that water to make that bowling ball be just able to float. So going back over to this picture here, 8. When I look at the 12er here, we had to add a bunch of salt to make the 12 pound just barely float. If you do the math on it, I think it ends up being something like 11.59 pounds. It's just right. So 12 was a little too heavy, so I added some salt, and that's why this is able to just barely float. And to be clear, there's probably some error tolerance in building these bowling balls. But so now I got a water balloon here. What do you think is going to happen when I put this water balloon in here? What do you think is true about the density of a water balloon? Approximately. So what should happen to it? Sink or float or what? Just barely float, right? And so this is making some sense. Now keep in mind, I filled this with fresh water, so that it's actually going to have a slightly less density, so some of it's going to be poking out a little bit, but yeah, that's why there's a little bit. There's also a tiny air bubble. Yeah, so there's a couple of things. Interesting, right? What's going to happen? Let's say I release this thing from rest now. Do Do you see it accelerating? So you could actually do a problem with the buoyant force where it's accelerating, right? You just take something that's less dense than water, right? You could actually have it. So I guess we could discuss that more in a minute. Yeah, we'll go there. Anyway, so these ones are just barely less dense. That's why they come back up to the top. All right, enough on that. All right, what else? Let's see where we want to go. Did we finish that problem, 14.17? I think we did. Let's take a look. Oh my gosh. Okay, you could determine the weight of the ball in pounds. So if you want to actually do this, now that we know the density of the fluid should be the same as the density of the object should be the same as the fluid. How would I get the weight of the object? If you wanted the weight of the object, how would you get that?
Density of the fluid times the
The weight would be also times G. So if you did density of the density of the object or density of the fluid times this, and so when you punch all that in, you can actually get a number and find out the exact weight of a bowling ball, which should float in fresh water. All right, I think that's enough. Let's look at 14.18. Another classic. We got this block of wood, and in this case, it's not fully submerged. So there's some fluid. That's my attempt to draw this. Now, in this case, let's see what we're given. We know it's X, Y, and Z. So this dimension is X, this dimension is Y, and this dimension here is Z. And we're told it floats in a fluid with density rho. Okay. It's solid. Got it. How does the buoyant force compare to the weight of this object? Which is bigger, buoyant force or the weight? When it's out of the water like that, floating. Same. It's being supported. It's not sinking. Buoyant force equals weight of the object. Next. Is the volume of displaced fluid greater than, less than, or equal to the volume of the object? How does volume displaced compare to volume of the object itself? How does volume displaced compare to volume of the piece of wood or whatever it is floating there? Yeah, so it's volume displaced is less than the volume of the object, right? Let's figure out this free body diagram. We've got a buoyant force up. We've got mg down. The buoyant force, we're usually going to describe this as density of the fluid, volume displaced times g. The mass of the object, we usually convert to density of the object, volume of the object times g. Is this pace about right? Or is it too fast, too slow? I'll give you a second. So when I do the FBDs, basically I immediately replace these. All right. Well, now in this case, acceleration equals 0. It's an equilibrium. That allows me to say density of the fluid volume displaced times G is density of the object, volume of the object times G. And now what I'm going to do is I'm going to try and describe this distance right here. That is some fraction. Did I call it Z or H? Oh, I called this H. And so we know that H is equal to some fraction of Z, or some percentage of Z. It's getting you used to the style and how these work out. Well, when I plug that all in, the main difference is on this side, the displaced volume uses H, or some fraction times Z. And notice what drops out. X, Y, G, X, Y, G. If I plug in that H equals FZ, I could even cancel out the Z. And notice the density of the fluid times some fraction F. Said another way, the fraction is the density of the object divided by the density of the fluid. Right? Well, and then let me see where I want to go with this. Okay, that's good. This tells us what fraction of the object will be submerged. So now let's think about this. Let's say this object was an ice cube. Does anybody know the density of ice? Approximately. Yeah. So I'm going to use grams per centimeter cubed. We could also use 900 kilograms per meter cubed. So in these units, you have something made out of ice. Notice that's 9/10 or 90%. 90% of the iceberg is under the surface. Maybe you've heard that before. And this is regardless of the weird shape that it takes, right? Now we've got to be careful here. You might get to the end of this problem and say, well, what if the density of the object is larger than the density of the fluid? Would this problem still work? If the density of the object was larger than the fluid, would this picture make sense? No. If the density of the object is greater than the fluid, it would sink and it would go to the bottom and we'd need a normal force. Got it? All right, how you feeling on this stuff? Okay? All right. Let's look at an application here. Take a look at problem 14.19 on page 137. 14.19, page 137. Let me do this. Just a little bit. There we go. All right. So imagine you have a crown or something that's a weird shaped volume, and you want to get the density of that object, right? So in this case, I'm going to use this. This would be an awkward object. We can figure out the volume of this, but you're going to be kind of annoying. We'd have to do a bunch of measurements and take some time and think about the corners and make sure we don't screw that up. But let's say I want to get the density of this object. Where did I put my scale? Come on now. Oh, there it is. We use this scale. We notice it's 0. Okay, looking pretty good. So what I could do is actually, is that showing up, Jules?
Yeah.
So it looks like this is about 6 newtons out of the water. Then what I'm going to do is put this in the water. Can you see the scale still, Jules?
Yeah.
Thanks. I'm just barely above the floor there. Okay, so I probably needed a little bit more water here. Okay. So again, it's not perfect, but it's almost fully submerged there. Okay, and I'm not touching the bottom. Do you agree the scale reading drops to about, oops, about 3.8 or so? If I touch the bottom, it goes to 0, right? So about 4. Cool? So we get 2 scale readings. And now my claim is, from this information, in theory, you could figure out the density. Let's look at the problem really quick. 14.19. Let me get some board erased here. I should do it over here. So here's the trick. First, you're going to weigh the object out of the water, and you get a scale reading. T is equal to mg out of the water. Is everybody okay with that? I'll call that T1. Right? Whereas when you fully submerged, is everybody okay with that? I'm not drawing the pictures, but you agree when it's fully submerged, the buoyant force is helping support the weight, and that's why we get a lower scale reading. Well, if I plug in, if I eliminate mg using T1, I get T2 plus buoyant force equals T1. And when I do that, let's do it this way. Buoyant force is equal to T1 minus T2. So the density of the fluid times the volume, in this case, is the displaced volume equal to the volume of the object. For this problem, was that true? It's fully submerged. Is it okay to use object volume or not? When it's fully submerged, yes. That's why it's okay. This should technically be volume displaced, but because it was fully submerged, volume displaced the volume of the object. So notice I can flip this around and solve for the volume of the object. And lo and behold, you could get something's volume using these 2 scale readings. That's what I wanted to point out. Does that make sense? This is a method used to figure out people's body fat percentage. Have you ever seen this picture or a video of this where you get a person and you put them in a swimming pool and you weigh them while they're in a little mini swimming pool? So you can actually figure out, if you know somebody's volume and you know their weight, right, you can get their density. And you can figure out what % of their body is fat versus muscle on average. And it's approximately accurate. There's a big problem with this with a human being versus a chunk of aluminum. What is it? What was one of the assumptions we made here with this object?
I'd say fully submerged.
Fully submerged, and we assumed that the volume displaced was the volume of the object. Now you could get a person all the way underwater. But what's tricky about that?
How do you measure the scale reading?
Now you can put a scale in the bottom, that's true, you can do that. It's complicated, they do that.
It's just a matter of breathing, right?
Breathing, when you take a deep breath, your volume increases. So usually what they do is they say, right before you go under the water, exhale as much air as you can. That way your lungs collapse as much as possible so that the volume is as accurate as possible. If you take a deep breath and you're under the water, that's going to be tricky, right? Because then there's this big hollow cavity and you're not a solid object. You're a hollow object. Different rules would apply. Does that make sense? So if you're going to do hydrostatic weight on a human being, they have to exhale as much air as possible, then sink to the bottom. Yeah, anyways, so you can read about that. That's cool. The other way they do it is with the electrical conductivity sensors. You grab these sensors and then you see how much electricity you conduct. And the conductivity of fat is different than the conductivity of muscle. But I guess this way is more accurate most of the time. Whatever. But it's awkward to set up.
Why don't have them just breathe through a tube there?
What's that?
Why not just have them?
Well, if they breathe through a tube, every time you inhale, your volume goes up and the scale reading will change. So the trick is you have to have them under there with as much air out of their lungs as possible, then get the measurement, then they come up and get it. Got it? Yeah, so it's a little goofy, but yeah. All right, that's cool. If you want more on that, you could do that problem. All right, let me see here. Look at 14.20. It turns out concrete is less dense than aluminum. Maybe you know this, but you could make a boat out of steel, so you could clearly make a boat out of aluminum, which means you could clearly make a boat out of concrete. There's a competition for concrete canoe building. If you are interested in this, check out the Concrete Canoe National Competition put on by the American Society for Civil Engineers. Now, I'm not going to recommend doing that problem in the homework, but I just put this in there. Cal Poly, I think, has won a couple of times. So if you're into this and you happen to be going to Cal Poly and you're really passionate about concrete canoes, do it. All right. Yeah. You could look at that solution if you do that, and maybe that would help you. Yeah, it's just annoying, but yeah. Ooh. Look at 10.20. 10.20, oh, sorry, 10.20 and a half. I'm not going to do this one, but I'm going to kind of give you a visualization of it, okay? So this is one that's exam level difficulty. You should put a star next to this one and see how it says 14.42 and a half. You should do 20 and a half and 42 and a half. Got that? Mark those down while I get this ready. Get this pipe. All right, so in this case, I just want you to try and help you visualize this, because I think that's half the problem in these damn problems, right? So imagine you have a chunk of pipe like this, right? So it's hollow. I just want to point out, when you put it in here like this, that's different than taping up the bottom with Flex Seal, right? You guys are so dumb, right? Flex Seal. So we can put some tape on here. And what's the point of putting the tape on here? What is that doing? When I put it in the water, do you get the same displacement? No, right? So now this is definitely not leaking too badly. Oh, just a little. But if I could seal this, if I had used Flex Seal, damn it. The idea is when you put this underwater, the volume would be different than when it's like this, right? So when you do it like this, the water is filling up the tube and you're just getting the volume of the cylindrical shell. When you cover up the bottom, the volume displaced relates to the outer diameter volume. Is that clear? So take the time to do that problem because these are the types of problems I get into on final exam day. Got it? Where there's some hollow logic just to see if you were paying attention if you did a couple of practice problems. Is that enough said? I hope so. So you can do this. Yeah, and notice there's a spring holding it up, and yeah, so that's a good one. And let me check 14.42 and a half. Look at that one too. Ooh. Yeah, 14.42 and a half is also tricky. That's page 146. Page 146. And then while I'm at it, on page 144, problem 14.30 and a half is good. So those are really good those are hard buoyant force problems. If you can do all three of those, you should cruise on the test. Okay. All right. A couple more things here, just for conceptual knowledge. Let's see how you do. Turns out fluids are I don't know. Once you get used to it, it's okay, but you have to think a lot. So let's do this one. Let's say I have a boat here. And oh, sorry, which camera am I on? Okay, thanks, Jules. For those of you that have a book in front of you, page 138, 14.21. We're going to do problems 14.21 and 14.22 conceptually here. Okay. 14.21. Okay. So you got the problem in front of you. I'll give you a second to read it. Read 14.21. Make sure you feel good on that. And after we do these, we'll take a break. Okay, are we ready? Let's take a look. Here's the short version. Everybody keep an eye on the volume displacement now. Because I added a little bit of water, let me take just a little bit back out. Remember I added some water a few minutes ago? Let me just take out a little bit. Let's make sure. Let's let this stabilize. Sorry, should have done that. But it looks to me like the water level is pretty close to the bottom of the tape at this point. Do you agree? That's going to be our reference level. All right. I'm going to put this boat in here. I'm going to add some iron ore. Okay. Now, clearly, to float this, we need a huge buoyant force. So that's why there's a massive volume displacement. And on the ocean, we're not going to see this because it's spread out over such a thin layer, but we can see it clearly that it's displacing volume in this tank. So the question is, when I take the iron out and drop it in the water, what's going to happen to the water level? Got the question? So again, I'm going to remove the iron from the boat, put it in the water, and let it sink to the bottom. What should happen to the volume displaced? What should happen to the water level in the tank?
Lower.
Why?
Because the thing in the middle,
The iron.
not putting on something.
Okay, yeah, I like what you're saying. You're on the right track. So let me ask you right now. Is the iron suspended above the floor of the tank right now?
Yes.
Yes. So do you agree the buoyant force has to be large enough to float both the plastic and the iron? When I take it out, what's supporting the iron now? Normal force and a buoyant force, agreed? But when it sinks to the bottom, the normal force is going to be doing most of it. And notice the volume displaced clearly is a lot lower. we're still displacing some fluid, not much of the boat, but still a significant amount for the iron. And so, yeah, when I don't need to float the iron, I need less buoyant force, I need less displacement. Good? All right. Now let's try this one. I got a boat full of wood. Okay, boat full of wood. When I dump all the wood out, what should happen to the displaced volume? Right now, we're right here at the middle of the tape, maybe 2/3 up. If I dump all the wood into the water, what should happen to the displaced volume?
Is it the same as the wood floats?
Yeah, exactly. We expect the same because you're floating this crap either way. Now it's going to be a little bit crowded in here. Gotta get the boat in there too somehow. I'm running out of room. Bigger tank. But there we go. Okay. That's it. It's just barely in there. Do you agree it's the same level? So yeah, it's tricky to do this one because, yeah, I'll leave it at that. This is the best I could do with the wood versus the iron. So is everybody cool with that? The reason it's different, the iron sank to the bottom, some of the buoyant force was replaced by normal force, that's why the displacement went down. All right, now let's try this. Look at the next problem. What is it? Looks like a raft. What's the number of the next problem? 14 point, what'd you say? 22, 14.22. It's this situation right here. I got a piece of iron and I got a raft, okay? Now this one, you're gonna have to look pretty close, but how do we start? With the iron on top?
Yeah.
Okay. So this is kind of the final challenge to make sure you get this. I'm gonna rotate this 90 degrees just because I think that looks better. Sorry. Okay. So we got the raft and the iron. The question now, if I flip it upside down, two things. What should happen to the water level of the tank if I flip it upside down? What's that?
It's like right.
Why?
It's the volume of that.
Okay. Does anybody have any other ideas? Let me ask you. It's floating right now, right? If I flip it over, is it still going to float?
Yes.
Do I need the same amount of force? So what should be true about the displaced volume? It should be the same. So, but something should change, right? It shouldn't be exact. So you're on the right track that something should change. How will the water level change relative to the raft? And I don't know if you can see this. Trying to bring this all the way over. Do you agree right now the water line is almost exactly at the midline between those two? When I flip it over, will I have more or less foam underwater?
Yes.
Okay, let's see. Well, what's your reason?
Well, the main thing is pushing the foam underwater is the piece of metal. Therefore, if the piece of metal is underwater, then the buoyant force.
The foam still has to support it though.
Yeah, but the buoyant force is going to be helping the foam.
Exactly. There will be a small buoyant force from the iron that is helping out the foam. And so we should need less foam underwater to get the same. Nice. You got it. Good job. So when I flip this over, it's pretty subtle. Do you agree you can't see much difference there? But there should be a little bit less foam underwater now. And so, yeah, if we let this really come to equilibrium and flip it over again. So right now, oh my gosh, it's so close to the water line, it's hard to tell. The issue is this. The piece of iron that we have in there is such a small volume it's hard to tell the difference in the change in displacement, agreed? So that's the issue, but you got it right. That was the conceptual reasoning. So flipping it back over, let's see. Gosh, it's hard for me to tell much difference. But yeah, maybe on camera you can see it a little better. Jules, can you tell the difference on camera a little bit?
I think so.
All right. It's very subtle, but you guys, that was the reasoning we were looking for. Let's see if there's anything else I want to talk about. Whoops. Okay. So I've already mentioned which problems would be good to practice for this at home. I think I gave you those already. Those were the hard ones. One more problem that's super fun, I think, is really cool, are the problems on page 139. I don't know if you remember, we discussed this where I could say you could think of yourself as swimming through a sea of air right now. And if you wanted to figure out the buoyant force, that problem 14.24, maybe don't do it, but read it and look at the solutions there. And then 14.24 and a half, we'll talk about how much string it would take to weigh down a helium balloon. So if you're interested in that, you can go ahead and do that one too. That's a pretty fun problem. I like it. That was one of my favorites. So 14.24 and a half. So summarizing there, did you notice anything with a half pretty much is good in this chapter? So maybe we could summarize that. Good problems. It was, just making sure you got these on record. 14.20 and a half. I think it was 14 point, what was that next one? 24 and a half, 22 and a half? Oh, 24 and a half. Oh. 14.30 and a half, and the other one was 14.42 and a half.
Yeah.
So if you could do all of those, you're gonna be ready on exam day. And just as a reminder, I think 14.17 is worth reviewing. I feel like we've kind of beat the crap out of the buoyant force. Do you? At this point, you do a couple of problems, you're going to be ready. Let's take our break and we'll come back and we'll start talking about fluids in motion. Okay, that's the other topic, fluids in motion. All right, so let's take that break. testing out some camera here. Probably have to scoot over to see this one, but. Corn syrup. See if that shows up okay. Maybe I'll just do this so I get more light in there. Does that look better? Yeah. Okay. Then shoot, I went the wrong way, so let me do this. See a red dot? A red blob? All right. Okay. All right, so we're going to start up on page 141, and I'll talk about that demonstration in just a second. Page 141. We're going to talk about fluids in motion now. Now, fluids in motion is so amazingly complicated. You need to take serious courses if you're interested in this. So obviously, like I'm thinking, Jules, you might need to take real fluids classes someday, because right when you're thinking about the fluids involved in astronomical situations, all right? Fluids and thermodynamics both are really tough. So what we're going to do so that it's not outrageous is we're going to restrict ourselves to some simple types of fluids, okay? And I'm looking at page 141. To fluids which are non-viscous, which is absurd, right? We're going to ignore drag. Now, you know this. You stick your hand outside the window, you feel drag. If you go swimming, you feel drag. So this is a little bit bonkers, but at least it gets us started. You got to start somewhere. If you want to add in drag, it's just so complicated, we don't have the time to do it. We're going to talk about incompressible. And if you remember from the glass hammer, that was constant density. Finally, we're going to only use laminar flow. So we're going to say no turbulence. This is absurdly simple. Anything in the real world is much more complicated than this. But just like when we ignored air resistance for projectile problems, even though it's hugely important, you can get a fundamental idea of approximately how things will behave. Now, just to show you how strange laminar flow is and how not used to it you are, I've got this demonstration up here at the front, and that's where I want to go to. So you may actually want to take a look, and I'm getting just the top of your head there, Edgar. I don't know if you care. Let's take a look at it. So those of you, you may want to come in close to see this, and I'm going to ask you to come up and actually look from the top in a minute. So if you want to get up here, laminar flow. Yeah, if you guys want to just come around, both of you there, you can come around to this side of me. Right? And take a look from the top. You kind of see that? Go ahead and look in there, look down. You see this blobs?
Yeah.
Okay, you see it? So laminar flow is a very unusual type of flow. Can you see the blobs all right? Okay, so now what I'm going to do, we got to count. I'm going to turn this a precise number of times. slowly. Let's see. I think that was 1. 2. 3. I'm trying to turn it slowly. Take a look in there again. Do you see the lines or lamina starting? Look down from the top. Get in there and look down. You see the lamina starting to appear? The layers? You see it looking like a striped cake or some kind of stripe? What was that? 3? Whatever. Let's keep doing this a few more times. So I'm mixing this and I'm trying to go slowly so that I don't get turbulence and we get this laminar flow. And if I go too fast, this will all screw up. I've stopped keeping track. Have you? Fortunately, 7? Okay. Jules, you want to see this from the top too, just for fun? We're getting close to 10, maybe?
That's 10.
Okay, so take a look in there again, and now you can really see the lamina, the layers. It's a layered flow. And do you agree it's starting to be pretty well mixed? We're starting to see a lot of red spread out.
Yeah.
This is the weird part now. I'm going to unmix it. See it starting to come back? I know this takes time, but I think it's worth it just because it's so weird. We call this reversible fluid mixing. So if your flow is truly laminar without turbulence, do you see it's back? Isn't that crazy? You can unmix a fluid. Isn't that trippy? Now, I'm starting to lose track how many I did here, but I think we're getting pretty close. Do you see the blob coming back?
Yep.
So you can actually unmix the fluid. Weird, right? That's how weird laminar flow is. Do you agree most flows in the real world are not like this? You can't unmix the Kool-Aid. So, all right, okay, that was all that was. I just trip out on that, and I think it's cool, and I wanted you to see it. That's it. Yeah, that's such a good one, huh?
Yeah, I know. I was just-
Angus is pretty good at setting that one up. He's got it down. So, yeah, anyways. The trick is you color the cornstarch, or the corn syrup, and you inject some food colored cornstarch to make the blobs after you fill it up. And obviously you got to have, so what we were doing there is we had these 2 cylinders, and so the outer cylinder was rotating and dragging it along. Clearly this is not the same type of fluid here. That was laminar flow, but it was clearly viscous. So you can see even, it's very difficult to find a fluid that actually behaves in these ways. Water's pretty incompressible. It doesn't have a ton of drag. And if it's flowing slowly, we can probably approximate it as laminar flow, right? So when we do that, we're going to make those assumptions, and then we need some terms. So I'm going to go back to page 141 and talk about terms. Okay. So just some definitions. Rho, that's going to be our fluid density. A is going to be cross-sectional area. That's what we've been using all along here. But just so you know, it's a cross-sectional area. R is a thing called the volume flow rate. B, lowercase, is fluid speed. And I want to point out there's a flow rate and a speed, and they're not going to be the same thing. I'll discuss how they're related. When a physicist talks about pressure in a moving fluid, strictly speaking, we probably should be saying static pressure, because there's different types of pressure in fluid flows. Stagnation pressure, dynamic pressure, static pressure, there's a bunch of different types. Lowercase q is going to be called dynamic pressure. And then P plus Q is a quantity known as stagnation pressure. And I promise I will try to make clear what you really need to know after we do a little bit. There's a picture up here. Let's say you have some fluid flow. These things are called streamlines. So you've probably seen an image of a car or an airplane in a wind tunnel, and there's literally fog machine running, and you see the lines of smoke, right? Those are the streamlines, okay? And maybe I'll put this one in here in red just so you can see it better. The cross-sectional area might be just some area that this is flowing through. So it's the area that the fluid is flowing through, okay? What else do I want to say? Anything else? We should probably put some units on these. The volume flow rate, this is one that's important to have the units. And what units did I want to use here? Well, the ones that you might be used to are probably gallons per minute. But you could also go to liters per second, or easiest for a physics class is probably meters cubed per second. So volume flow rate is literally how many gallons are flowing through a pipe every minute, which we could rephrase that as how many meters cubed every second. And so we're going to use meters cubed per second in this class. Cool? And sometimes this word is shortened to just flow rate. Just like this one is sometimes shortened to just pressure. So you're going to hear me say flow rate, and I'll get lazy and forget to say the word volume. So when I say flow rate, I mean this term, volume flow rate. When I say pressure, I mean this term. Fluid speed, what are the units of any speed? Meters per second. So that's how you can sometimes tell the difference. Speed is literally how many meters per second one molecule is moving as it travels along these streamlines. Volume flow rate is the amount of volume per second passing through that surface area. Okay, what else? What are the units of pressure for a physicist? You remember? Pascals. And a Pascal is equal to what? A Newton over meter squared. Force per unit area. Force per unit area. All right? Now, here's what I like to think about with these things, right? When you have fluid, and let's just say you're sitting right here in one chunk of the fluid. Let's say you look at this one little box of fluid right here. There's pressure in every direction. Okay? Remember that? We talked about this, the pressure points in every direction. So I'll call that the static pressure. That's the pressure in this case that is perpendicular to the fluid flow. The dynamic pressure, Q, is in the direction of the fluid flow. So I like to think about it like this. When you're drinking from a fire hose, the pain is the Q, right? Imagine if you just stuck your mouth open and tried to drink from a fire hose. You would be knocked backwards. That amount of pressure that you're feeling is Q. That's in the direction of the fluid flow. But that doesn't mean there's not pressure perpendicular to the fluid flow in every direction as well. That's not what's hurting you. Now, and being clear, there's going to be some of that pressure P forwards as well. And that's what this P plus Q is talking about. If you were trying to drink from a fire hose and stop the fluid, you would have to stop both the pressure or static pressure and the dynamic pressure, right? So the stagnation pressure is the pressure required to stagnate the fluid. which is both of them. Is that making any sense at all? Maybe? Can you get the lights for me? Right up there, just go and turn off all the lights.
Is it like putting your thumb on
If you put your thumb on the end of a garden hose and completely stop the fluid, you've stagnated the fluid flow. Yes. Just turn off all of them, yeah. Can you get that last one? Or yeah. Just kind of flip every switch until that one goes off. Just check it. Or I can get it. So, some of them you gotta flip up. There you go. That's it. Thanks for doing that. That just saved me a little bit of time. Let me get this on Zoom here. All right, so you guys can see this okay?
Yep.
So we've got a pipe and some fluid flowing in it. And let me just try and label some of this crap. This puppy up here, liters per second, what symbol is that? Flow rate. You remember what symbol I used? R for rate. So that's how many gallons per minute or how many meters cubed per second. We'd obviously have to do a conversion. All right. Now, speed, on the other hand, would be how fast this molecule is moving right there. All right. Now, what do you notice about the speed in the middle of this pipe here? Lower. How about right here? Larger. And there. So now let me ask you this. Which region of the pipe has the largest dynamic pressure? I'll give you a hint. The symbol was Q. That's dynamic pressure. Did I give you a formula for that? I don't remember if I did. Yeah, it's 1/2 rho V squared. So G, which region of the pipe is going to have the largest dynamic pressure? Is it A, B, C, or D over there? Yeah, right. And so this region, well, we could actually look at these two. These are the two most interesting. So we've got maximum and minimum dynamic pressures there. Agreed? And then maybe what I'll do is, let's do this. I'm going to wait for this to flow out. I just took the dots away. Give me a second. Okay. So now what I can do is if I push this button, we'll see what the fluid flow looks like if the particles were organized. And so what happens here is when the pipe gets wider, they can spread out and slow down. When it gets narrow, well, let's do that again. They're going to let me do another one. I just think that looks cool. Right? And so when the pipe, you've probably seen this in a river. Right? If you've ever looked at a river, wide sections of the river, the flow rate, the speed is very slow. Now notice at every point in the pipe, they have the same gallons per second. When the pipe is wider, you don't need to have as much speed to get the same number of liters per second or meters cubed. So if I say it this way, right here, there's a large area. I'm going to call that area 1 is big. Right? And there's a speed here, V1. Whereas over here, we've got area 2, a lot smaller, and we've got V2. Both of these need to have the same amount of fluid flowing through them per second, but the speed can be different. They need the same meters cubed per second. What are the units of A1 times V1? What are the units? Or A2 times V2? Check the units. What's that going to be?
Meters cubed over second.
Yeah, that's the flow rate. Assuming the pipe is not leaking, we should assume that rate 1, the volume flow rate, equals rate 2. So we see that A1 V1 equals A2 V2. Again, this is for an ideal fluid, More in your real fluids class later. Does that make some sense? Well, you could see if the area gets big, whoops. That's say area 1v1, shouldn't it? Sorry about that. If the area is big, the speed is small and vice versa. Good? Now we could talk about this. Let's look at the pressure in here. The pressure at this spot, oops, let's try and get them right on the center line. Do you agree that the pressures are not exactly the same? Let me clear those annotations. Do you agree that the pressure is not the same at each spot? Right? What's going on there? Notice when the fluid is going quickly in the tube, what happens to the pressure? It reduces. I like to think of it this way. The fluid is coming in. You only have so much pressure to go around. Okay? If you increase the dynamic pressure by increasing the speed, you must decrease the static pressure and vice versa. Does that make sense? All right. So now the reasoning that I'm describing here is only applicable to closed systems, pipes. And to be fair, what am I going to try and do on your test? Give you a pipe. So this is relating to like your final exam question. So that's okay that we're talking like this way. I cannot stress this enough. Do not blindly believe this is true for every fluid in the universe or every fluid system in the universe. Okay, if you have a closed pipe, if the fluid speeds up, all right, the pressure should drop. Now remember, when I say pressure, I mean which type of pressure? Static or dynamic? Static. So static pressure, perpendicular in every direction, drops. Dynamic pressure goes up. Cool? How are these terms feeling? Thumbs up, thumbs down. Just let me know where you're at. Okay, got it. All right, what else did I want to say here? Oh, now in the real world, not every pipe is perfectly level. So let's try another example here. Let me get these out of here. All right, let's do this. So let's say this is supposed to be a model of like a water main or something, right? Get this just okay. All right, there we go. So in this case, yeah, whatever, that's pretty good. All right, now when we run this thing, I'm curious how the depth is going to affect things. What do you know about pressure and depth? More depth, more pressure. What do you know about speed from a conservation of energy problem? When something goes downhill, what usually happens to the speed? So now we have a conundrum, right? When the fluid goes downhill, you expect its speed to go up. But when its speed goes up, you expect its pressure to go down. But when you go deeper, you expect the pressure to go up. Which wins? You see the conundrum we're under here? So in this case, there's a new relationship that we want to describe. Pressure versus depth is no longer valid if the fluid is moving, right? So if you have a moving fluid, there's a number of factors involved. There's the loss of gravitational potential energy, which is converted to kinetic. There's also these areas and all this stuff. So let's write one equation that will govern all of this for us. Okay, so I think that's enough on this. Does anybody need this simulation anymore right now? All right, let's close this up. Can you hit the lights for me again? Thanks for doing that. I appreciate it. So for fluids in motion, we have these two main equations. They are listed for you in the big boxes on page 141. I'm just going to write them here just so I have them all on one board. Okay. So we have these two equations. This upper one is called the Bernoulli equation. And this other one is called the continuity equation. And we are going to use these a lot. In particular, these are great for closed systems. And they're these equations that we're assuming, we're going to apply them to these ideal fluids, which are a huge approximation on real life. Okay, huge approximation. I want to focus on this Bernoulli equation. So I'm going to write that up on top of the next board and talk about that a little bit. Oops. I'm going to leave a little space here so I can make a comment afterwards, but I'm going to write this. Oops. I'm going to write it out in a different way here. If something is constant, basically, if I sum them with a 1 subscript, that should equal them summed with a 2 subscript. Does that make sense? So you pick 2 spots in the fluid. So right here could be spot 1. There's going to be a velocity 1. There's going to be pressure 1. And now what does H mean? H is not depth.
The initial reference level.
We're going to put a height or a reference level. Huh. Maybe you can see, doesn't this look a lot like an energy equation? This is an energy equation per unit volume. What is mass divided by volume? Density.
Oh.
So this is 1/2 mv squared divided by volume. What is mass divided by volume? So this is gravitational potential energy divided by volume. What is pressure difference? Force per unit area, you get a density. Okay, so it turns out pressure times a volume gives you work. Let me do a side problem here. You agree that force due to a pressure differential is equal to that pressure differential times an area? And do you agree that a force times a distance well, a cross-sectional area times a distance is a volume, but force times a distance is work? Basically, this is the work energy equation, and the pressure is the term doing the work. So what I wanted to say here, the Bernoulli equation is an energy equation per unit volume. As a result, H is height, not depth. Otherwise, this equation doesn't make sense. So we're going to pick a reference level here. And this would be height 1 to the center of the column. Right? We could say height 2 is equal to 0. Whoops, this is supposed to be light blue. Sorry. Is this making any sense at all? The idea is we're going to do conservation of energy for fluid flows. That's it. This is our energy equation. If you care, I did this very quickly, but essentially you can see that a pressure difference appears. That pressure difference relates to work done for a unit volume. I'm going to leave it like that. The units work out, and yes, I should have derived it more slowly, but I don't really care. I want to focus on using this equation. So far, so good? Down here is going to be V2 and pressure 2. So now we have all the tools we need. If you know the height, pressure, and speed at one spot, hopefully we can figure it out at the other spot. We should not use the pressure versus depth equation. So the pressure versus depth equation is valid for stationary fluid, but notice you never need to use this equation again. Bernoulli's equation gives it to you already. If you have a stationary fluid, what is the V for a stationary fluid? What is the fluid speed if it's stationary?
Sure.
Boom, boom, you got it. So notice there it's pressure versus height instead of pressure versus depth, but same idea. If the V terms drop out, right, one of the heights would be 0, you're going to get pressure versus depth back. Okay, so I don't like to use this equation ever again. I would only use this one all the time. That's just me. But if you like it, go for it. Do whatever you got. So far, so good? All right. Let me see where I want to go with this. So we'll have to get to some of the crazy demos next time, which will be fun. While we're eating pizza, we'll just do crazy demos. Let's take a look at Let's take a look at 14.28, page 142. I need to erase the board. So start looking at that. Look at 14.28, page 142. I'll try and hurry this up. Put a star next to this problem. Do it again after you leave class. Okay. Put a star next to this problem. Do it again after you leave class. That way you understand a lot of the assumptions that are common in these problems. They were racing. All right, good enough. We've got cylinder. The cylinder is sitting on the ground. And then there's a spout somewhere on this cylinder here. Okay. We're going to assume that there's a water column in here. So this is filled with water. And then you know from experience, the water is going to come shooting out. It's going to land over here somewhere. Okay. We're told that the entire, and what problem was this one? Sorry, 14 point what, 28? Thank you. What page?
142.
142. Okay, thanks. We're told that the height of the water column is capital H. What is this height? Is this little h or is this y? That's y. So this height is distance y. So I hope you agree that this distance right here should be capital H minus y. Is everybody cool with that?
Yep.
The diameter of the top is capital D. The diameter of this hole at the bottom is going to be little d. And we're going to make the assumption that the upper diameter is much, much bigger than the hole. This is crucial. Okay, I'm going to try and go through this in order. Now, oh, and then finally, this distance here was called x. Our goal in this problem, here's the big picture. Where do you think we should put the spout so that the water shoots out as far as possible? If I want X to be as big as possible, where should I put the hole? What do you think? Top, bottom, middle, somewhere in between? What do you think? What's your gut tell you? Where should you put the hole so that the water flies as far as possible? Okay, why is it advantageous to put the hole near the bottom?
Because all the water on top is.
You have a greater height. What happens to the speed as you go deeper? It should go faster. But if you're close to the ground,
Yeah,
it's going to hit the ground sooner because, right, it's only 1 centimeter off the ground. So what's the advantage of being near the top?
More distance traveled, but less speed.
Yeah, you have less speed.
So I guess the middle.
Maybe in the middle. So isn't this an interesting question? There's clearly a trade-off. You get more hang time up high, but less speed. So where is the right spot? So that's our goal. That's why this problem is kind of fun. And I actually have a pipe sitting over there. See the black pipe? We'll get to it in a minute. In that orange bucket, we're going to do it in just a second. So let's get through this one and call it a day, okay? Now, in this problem, you remember I said we're only going to use Bernoulli's equations for a closed system, but there's a hole at this end and a hole at that end, but everywhere in between, we're assuming no leakage. So that's why it's okay to view this as a closed system, okay? Right? This is like the pipe. Here's one opening to the pipe, here's the other opening, so everything in between, all right, is a closed system. Okay. You agree this fluid is open to the air at the top? It's an open pipe. What's the frickin' pressure at the top? Atmospheric pressure. Are you okay if I write P0, atmospheric pressure? Now wait a minute. What about right here? What's true about the pressure here?
Also atmospheric.
It's also atmospheric because there's air in contact with it. So far, so good? Now, I'm going to label everything at the top is going to be a number 1. Everything down here is going to be a number 2, just so I don't have to write whole and top all the time, okay? So basically, I'm going to say this is pressure 1. I'm going to call this pressure 2. Is everybody okay with that? Because 1 is every subscript at the top. All right? And let me see where I want to go with this. Okay. There's 2 equations we almost always use. The continuity equation tells us area 1, speed 1 equals area 2, speed 2. In this case, let's solve this for speed 1, the speed at the top. What's the equation for areas in terms of diameters?
V squared over 4 pi.
Yep, that's it.
Yeah.
Do you agree that area 1 is the big one with the big diameter? A2 is down here, uses little diameter. What cancels out? Constants. Okay, so notice. Jules, if they keep playing, will you shut the door if it happens again? Thanks. All right, so check this out. Do you agree the speed at the top is going to be what? Bigger or smaller than V2? Yeah, and if D is much bigger than D, do you agree it's going to be hella smaller? Look at this thing. I got a small number over a huge number, then I square it. So let's say the ratio is 1 to 10, right? Then the speed would be 100 times less. What does that mean? As water's coming out of here, how quickly will the water move downwards? If you have a tiny hole, the fluid level is not going to decrease that rapidly. That's what that's saying. Does that make sense? What we're saying is V1 is approximately equal to 0. So if I fill this thing up, poke a hole in it, the water's not going to drain out that fast. That's part A. Okay. Okay, so part B. Now I'm going to use my Bernoulli equation. I know pressure 1 plus rho G H1 plus 1/2 rho V1 squared, or dynamic pressure squared, which terms drop out?
Pressure 1, pressure 2, because they're both 1 atmosphere.
Exactly. Here, these are both 1 atmosphere, or about 10 to the 5th pascals. So they're going to drop out. There's another term which drops out. Now think about this. V1 we already know is small compared to 2. So think about it. Now when you square it, it's going to be even smaller. So it turns out, at first it looks like these diameters need to be very different. If this is like 3 or 4 times bigger, all of our assumptions are going to be valid, because you get a 4th power in this term, right? So 3.16 to the 4th is about 100, whatever, something like that. I forget the exact numbers, but right? Okay. Square root of 10 to the fourth is about 100. All right. Now, can we just pick an easy reference level? How about the bottom is height equals 0? Is that showing up, Jules? Yeah. Okay. So if the bottom is our height, what's the height of object 1 or surface 1? Excuse me. Capital H. Height 2 is no, it's the whole.
Oh,
It's y. You rearrange this, g, we get v2. Well, what term drops out? What's in every term at this point? Density. Density drops out. We get v2 equals the square root of 2g h. Remember that? The fluid speed is equal to the square root of 2gh minus y. That's the distance the fluid has fallen. Just like dropping a ball. If you drop a ball distance h minus y, the speed would be this. Cool? All right. So that's the speed. How would you get x? I'm going to push through this real quick. Let's just finish this out. How would you figure out the distance x that it flies? What type of problem would you do? Kinematics. Notice delta y is negative y. A sub y equals negative g. B initial y equals 0. B initial x equals that garbage. B final x and a sub x. What's a sub x for kinematics? 0 for projectile. So what does that make V final x? The initial x. Do you remember all this crap? What else? I should have written. We don't know the time. We don't know V final y. 1, 2, 3, 4, 5, 6, whatever. Oh, delta x. We do know that. What would you do? Write some equations, right? Well, in this case, I think I could get the time using this, right? In this case, this term 0, negative y equals negative g over 2t squared. T, the minus 2y over g square root. Time is positive. I don't need to plus or minus. You guys agree with all that crap? Then I plug this into the x equation. I don't worry about the 1/2 a sub x because a sub x is 0. Delta x is x. The initial x is this garbage. Time was what cancels out?
G.
G. So we get it's got the right units. How do I figure out the maximum value for x? What do we do with every function if we want to maximize it?
Derivative.
You can take a derivative. We don't say derivative, say take a derivative of it, but you got the right idea. Yeah, yeah. You can take a derivative of x with respect to, no, not h. Y is the thing that we're free to vary, right? We said, where should I put the whole?
Constant.
This is the variable. H is, yeah, so you can do that and see. What do you bet you get? What did you say at the beginning you thought you would get?
Right in the middle.
Halfway. Let's just run it really quick and get you the hell out of here. All right. that on screen, Jules?
Yeah.
Okay. Right. Maybe what I'll do is this. All right, gonna get a line check real quick. Sorry, I know you're ready to go. Let me just get this. You can see the bottom. There's gonna be 3 holes in there. 3/4, halfway, 1/4. The water goes pretty much all the way to the bottom here. So we're gonna split it. Oh. See it up there? All right. We'll do this real quick. Jules, am I on screen?
Yeah.
Okay, so now I'm just gonna rip all 3 holes at once. You agree the one in the middle goes a little bit farther than the rest?
Yeah.
All right. You can do the math at home. Oh my goodness. If you're curious, right, it's only gone down about this much. Only gone down about 1 finger after all that. So the assumption that the speed at the top is good. Now gradually as the fluid's flowing down, this should change. I'll just leave that good. Get out of here. I don't know if you can't see that at all on Zoom, can you? Shit. Can you? Okay, you can see better than me. But yeah, okay, so. Yeah. That makes it show up right. I don't know if you can see it better with this. Jules, does this look better? Yeah, now the water, you want to fill up the top off the bucket? Does that help it?
Yeah, a little bit.
All right, just top up the bucket. You guys can get out of here if you want. It's tricky, right? And just fill it up, fill everywhere, I don't care. Okay, there we go. That's good, that's good. Now can you see it better?
Yeah.
And then it obviously gets a little bit tricky. If you go all the way to the surface here, that's different. We got to go just to this level. All right, so I don't know, it's pretty close between the top 2. All right, that's it. Go ahead and get out of here. If you're curious, you can look at it. If not, get out of
The
here.
water, are you just gonna drain it?
I'll figure it out in a minute. I don't know what I'm gonna do. I better figure that out quickly though, huh? I just wanted to show you the demo.